we talked about curvature, Gaussian curvature for a two-dimensional surface, and in particular, talked example a flat plane, which was the curvature equal to 0, and talked about a spherical surface or two-sphere, which is the curvature equal to 1 over r squared. R is the radius of the sphere. Now, all these are examples of surface of constant curvature. K is a constant, 0 over r squared. Turns out it's also possible to have something called a pseudosphere with a negative curvature. In that case, it turns out the Gaussian curvature is equal to minus 1 over r squared. So therefore, we can collectively write the surface of constant curvature as Gaussian curvature equal to a lowercase k over r squared. The lowercase k is called the curvature signature, which can be +1 for sphere, -1 for pseudosphere, 0 for a flat plane. Now, there's no simple way to visualize the negative curved pseudosphere because its natural embedding is not in a three-dimensional Euclidean space, but into a three-dimensional pseudo-Euclidean space with symmetric for that 3D space equal to 1, 1, minus 1. In fact, the embedding condition in such a pseudo-Euclidean space is x squared plus y squared minus z squared equal to minus r squared. This is in contrast to the spherical embedding in a three-dimensional Euclidean space is x squared plus y squared plus z squared equal to plus r squared. Now, we cannot draw the whole pseudosphere in ordinary 3D space, but the closest we can do is to find a two-dimensional negative curvature space is central portion of the saddle surface. Turns out that portion here is negative curves. Now, let's collect all the formula for the curvature for two-dimensional case. Instead of writing the matrix, I'm just writing the invariance distance squared. So ds squared gab dxa dxb, and gab is diagonal is only g11, so x1 squared g22 x2 squared. For this surface constant curvature, turns out they can be collected written together in similar form like this. For example, for the flat plane, instead of writing Cartesian, but in terms of polar coordinates, ds squared is dr squared, and r squared d phi squared. R phi are polar coordinates. And if I choose to divide by some factor, big R squared, so this the first term is dr over lowercase r over capital R square, and the second one is of course the same way. Okay. Now, if we write small r over big R as chi, therefore this can be written as this one here. Okay. But for spherical surface, we have in the polar coordinates, if r squared d theta squared r squared sine squared, this segment here, d phi squared. Again, we choose to write doing the fact the theta is equal to small r, which is the radius over there, times the radius of the sphere. Okay, right? This is the angle, polar angle defined to be the ratio of the arc length divided by radius, and then this can also be written this way. So this is this expression here, and it turns out for the pseudosphere, they simply change sign to hyperbolic sign. Okay. Now these three expressions can be collected in a compact way like this. the ds squared equal to r squared d chi squared plus 1 over k sine sine squared for argument being square root k over chi. And you can easily check knowing the fact for example, k equal to 0. So when k gets small, this sine is equal to just argument, just angle, which is square root k. Then square is just k. So k cancel. That's get return. It recovers the expression for this. And for k equal to 1, of course, this is definitely just obviously true. But for for negative curvature, k equal to minus 1, and you have k square root minus 1, that's equal to I, and the sine of I is equal to I hyperbolic sine. So again, because you have a sine here squared like a minus 1, just cancel the minus 1 coming from 1 over the signature, curvature signature minus 1 in the denominator. Now that's for the 2D surface. What about 3D surface? Okay. Now let's remember for 2D flat plane in the polar coordinates, r phi is with the metric is this for, which is written down last slides already. Now compare that to 3D flat space in the spherical coordinates, r theta. Basically, you have extra degree in polar coordinates. Then the metric you can check equal to dr squared r squared over d omega squared. Omega is the element of the solid angle equal to polar angle squared plus sine squared theta d phi squared. Okay, just differential solid angle. So this case, of course, for k equals 0, 2D and 3D k equals 0 space, and you just go from just replacing the phi by omega, by the solid angle. And so this suggests the same thing works for replacement for all k, not only k equals 0, but k equal to 1 and minus 1. Okay, turns out that's the case. So remember, we had two-dimensional, we have the constant surface, we have so therefore, to find three-dimensional case for the polar angle is exactly the same thing, except now you're replacing phi by omega. And similarly, for the cylindrical coordinates, for a dimension radius of the cylindrical radial distance divided by the this radius curvature, you will find this for, again, different value for all k, just for k equals 0, minus 1, plus 1. Okay. So this is how to write a three-dimensional surface, a three-dimensional space with constant curvature. Now, curvature measures the deviation from Euclidean relations. For example, the relation between radius and circumference. Okay. Now we have s equal to 2 pi r, but if the r, if the spherical surface, then the r is on the surface, so it's not this distance, but it's the arc length on the surface, and then the circumference s is related to r. It's not 2 pi r minus s equals 0, but rather it depends on proportional curvature k. And for this will be 1 over r squared, the radius. And for also works for, so therefore for the spherical surface, or rather 2 pi is larger than the circumference s. And for saddle surface, it will be less. Another way to see, to show that the Euclidean relation changes for a curved surface is something called angular excess of a polygon, in particular simple triangle, which is the difference between the sum of the interior angles and the Euclidean value. And this angular excess, it turns out to be, is proportional to the area of the polygon with proportionality given by the curvature k. So it was angle excess is equal to k times the area of the polygon. In particular, the simple case, the triangle. Let's consider a particular, not only triangle, but a particular simple triangle. A triangle on a spherical surface with each interior angle to be 90 degrees. Okay. And so this has angle excess will be minus 180 degrees. So the angle excess is 90 degrees. So this satisfy this 90-degree pi over 2 satisfy this relation because the area of this 90-degree triangle is 1/8, right? 1/4 of the hemisphere, so 1/8 is spherical area. Spherical area is 4 pi r squared, so divided by 8 is pi r squared divided by 2. So that's sigma equal pi squared. And then multiplied by the curvature 1 over r squared, just cancel this out. So you could pi over 2 is just angle excess. Turns out this angle excess can also be measured in inspection like this by an operation called parallel transport of vector around the polygon, in this case triangle. It was our parallel transport vector around this triangle. I have a vector starting from the lower left corner, so vector 1, then I parallel transport up to here, so that's point 2. Then I parallel transport along the second side of the triangle to become vector 3. Then I parallel transport back to original position. So you notice this vector changed from point this way to here. So I rotate by 90 degrees. And that's a way related to the angular excess. So that's one way to measure the angular excess is by parallel transport a vector over the closed path. In this case, triangle. Of course, you can triangle for more complicated polygon can always divide into triangles. So now this is all talking about curvature in two-dimensional space. For higher dimension, Gaussian Riemann came with the formula for curvature for high arbitrary dimension, and it's a complicated looking thing. It's a tensor with 4 indices, so it's a tensor of rank 4. It's equal to the derivative of the Christoffel tensor and square of the Christoffel symbols. Okay, it's 4 indices, so each side you have the matched index, mu, lambda, alpha. So of course, Christoffel symbols are first derivative of the metric. So therefore, this is a nonlinear second derivative of the metric. Okay, because I have squared this, and they have linear term, square term. So it's a nonlinear second derivative. In fact, we'll see one way to derive the Riemann curvature tensor is by generalization this two-dimensional relation between angular excess and the area, and the proportion constant being a curvature. Okay. So we'll find that the change of vector axis can be measured by parallel transport, so that we can simulate by finding the change of vector due to parallel transport around closed path, in this case infinitesimal parallelogram. The change vector dA is proportional to the vector A itself and proportional to the parallelogram, the area spanned by the infinitesimal A and B. So this is sigma, and the proportion constant we call the Riemann curvature. So the angle is dA over A, so therefore dA is proportional to A plus. So this is really basically the same formula to higher dimensions. So anyway, this proportion constant with 4 indices is a rank 4 tensor, and because we see the area is antisymmetric, so therefore this lambda 2 indices must be antisymmetric. Okay, the takeaways of lecture 12. We learned that geodesic equation is the equation of motion in GR. We only derived this heuristically, but later on we'll give more formal derivation. And this is with a particle trajectory in space-time is a geodesic in four-dimensional space-time. Not to be confused, it's not a geodesic in 3D space. And the Newtonian limit corresponds to a particle moving with non-relative speed and a weak and a static gravitational field. If I apply this limit to the geodesic equation, we cover the equation of motion in Newton's theory. And then we start looking for the field equation in GR, which is called Einstein equation. Its structure can be inferred from the Newtonian field equation and from symmetry, and this way you can fix the tensor structure. Okay. And the Gaussian curvature is a coordinate-independent criterion to decide whether the space is curved or not. And the space of constant curvature with this signature k plus 1 minus 1 0. And the high dimension in particular, high dimension curvature, so-called Riemannian curvature, is proportional to terms involve the first derivative of the Christoffel symbol or square of this crystal symbols. So it's a linear second derivative with involving the second derivative of the metric square of the first derivative. And next lecture we could talk about why if the metric is the gravitational potential, then the curvature is directly related to the tidal gravity. So first we get a qualitative discussion of tidal forces, then we'll talk about the mathematics describing a tidal force. And then we'll talk about Einstein equation, and we very brief mention gravitational wave.